copy a lot of slides over though. Yes.
So was sapling still due on Monday?
I don't remember. Did I have it set to be due Monday? Yeah. We'll see how far we get. Yeah, we'll see how far we get through the alcohol chapter, and I may push that back further. It was a really long assignment, so I have no problems pushing it back further. We'll kind of see how everybody's doing with that. From what I've seen, the most that people have done, I think, has been 30 to 40 questions, and we'll just kind of see what happens. The idea is that it gives you that practice and it reviews a lot of old stuff, which is why it's a lot longer, particularly for those people coming from Chandler Gilbert who missed a lot of that material. It's going to be helpful to have that practice before you see it show up on the exams.
So my other question is the exam still scheduled for the 28th?
I will not change the exam due dates. I will shift homework due dates around. And because the homework is nothing like where I wanted it to be, I might just push it all to the 2 or 3 days before the exam, so that way you've got that full time to do it. The reason why I hesitate doing that is then usually most of the class waits till the day before the exam to finish the homework. So that is a possibility for happening, but I'd prefer you work on it faster. All right. Other questions? Okay, so a slight change on how we're looking at the functional group. So what we're going to do is, for future presentations as well, we'll start with kind of going through the same kind of breakdowns for each functional group. We'll look at naming, typically some acidity, though the acidity may shift to being towards the tail end of the functional group discussion because sometimes it gets more complicated. And then the repercussions thereof. So for the alcohol chapter, your repercussion of acidity is chapter 14. All the functional groups discussed in chapter 14, or most of them, come from alcohols being acidic, okay, or basic. We'll then go through and look at synthesis, so how can we make an alcohol? And in certain circumstances, we may add an extra little thing here. In this case, we'll look at how we can avoid reacting in alcohol. So if there's an alcohol present, can we prevent it from reacting and allowing us to do something else? And the very last thing we'll do is look at the reactions of alcohols. So now that we have an alcohol functional group, where can we go from? So with our acid-base characteristics, pretty sure we covered this. We looked at having them react in these equilibrium reactions, which means we're primarily, well, actually, equilibrium would suggest that we favor one direction. Most of these reactions, we tend to favor our starting materials. Okay. In both these cases, which means we don't really get anything particularly productive out of either of these two cases. Okay, so if we're going to try and get our alcohol to do some interesting acid-base characteristics, we want to push that equilibrium a little bit more. So in the case of having it act as an acid, we want to react it with a relatively strong base. Sodium hydroxide is not good enough. So the two big bases that are typically thrown in would be sodium metal or sodium hydride. They're both doing the same thing. Sodium metal does it in 2 stages. Sodium hydride does it in 1. Okay, so they're both going through and removing that hydrogen, the acidic hydrogen, off of your alcohol functional group. Okay. That acidic hydrogen. When we go through and look at having our alcohol act as a base, we're going to look at this one. Our alcohol acting as an acid, we'll look at the repercussions of that largely in chapter 14. When we look at our alcohol acting as a base, we're going to look at the repercussions of that in this chapter. Okay? Because what is the result? If we go through and look at that, what happens at the very end? What do we have out here? It is an ion, because we got that positive charge. We also, if we look at just the formula, have water. Water is incredibly stable, which means it is an incredibly good leaving group. So if we can get our alcohol to act as a base, we can make a leaving group and now make the alcohol do some other chemistry. Okay? So to do that, we'd want to react it with a strong acid or any one of our strong acids, but some of these acids can bring in complications. What do I mean? If we take a look at H2SO4, or in all of these, we get our H+, and then we also get a counterion, sulfate, chloride, bromide. The complication with this is that chloride and bromide not only are the conjugate base of our acid, but they are also really good nucleophiles, which means if we add HCl or HBl or HBr to an alcohol, we do get that acid-base reaction, but then it might be followed up with a substitution reaction, where we end up losing the water group in favor for bromide or chloride, because they're relatively good nucleophiles. So if we want our alcohol to just act as an acid and then do some other chemistry with it, we want to make sure that we limit the presence of a nucleophile. To do that, our standard acid is sulfuric acid. All right, so just kind of be aware of that. If we're just trying to get it to act, our alcohol act as a base, sulfuric acid is our best option. All right? And then we can kind of limit the side reactions as best as possible, or at least the side substitutions. The next kind of concept to get through is, can we alter acid or base strength? So there's varying things that you could go through, and in theory you guys are fairly comfortable with all of the things that control your acid or base strength. Typically, when I go through and think about acids and bases, I go through and try and think of the simple definitions. So a stronger acid wants to steal electrons away from hydrogen. Right, that means the electrons have to go into the structure, away from hydrogen. Okay, if they go into the structure, if we take a look at our conjugate base, what we're saying is that that A minus is now really stable. Right? If it is stable, then we can pull that H plus off relatively quickly and easily. So when you're trying to rank acid strength, look for the stability of the conjugate base. Okay? You can go through and rank those, at least from my perspective, easier than trying to rank at the ability of any one of those individual atoms to remove electrons from a hydrogen. That, to me, is a little bit more difficult to interpret. If we look at the converse, we look at trying to rank base strengths, we want the opposite. We want our basic atom to not stabilize electrons. The electrons need to have only one option, and that one option needs to be leaving the structure to react with H+. If that's the case, then it will react as a stronger base. Okay, so a lot of the simplification, or a lot of the things that you'll see, will come back to atom size, atom electronegativity, resonance, induction. Okay? So what you'd be doing is evaluating those in each particular case to evaluate your effects. When you go through and try and rank, you always start with rule number 1 and work your way down. Okay? A size difference has a much larger contribution to the acid or base characteristics than does induction, okay, in most cases. So we want to start with size first and slowly work our way through until we find a big difference between them. As examples, okay, let's take a look at, yes?
You're looking at the size of the conjugate base.
We're looking at the size of the atom that holds the charge, which could translate to being the size of the entire conjugate base, or it could be just an atom within it. Depends on the structure you're looking at. So we could look at, say, these. If we compared the acidity for our first two compounds, what we'd want to do is look at the stability of our conjugate base. So draw the conjugate base. Drawing all our lone pairs. We could look at the other one. Same idea. And what we're going to try and do is now compare those two structures and decide which one's more or less stable than the other. So the first thing we'll do is identify where is it most unstable. Well, biggest red flag is to look for charge. The oxygens are negative in both cases, so we'll start there. Our negative charge is held on an oxygen atom. What's the difference in size between an oxygen and an oxygen? Nothing. Okay? So this is where it comes back to how you're evaluating the size. That's your size. It's where the negative charge is. I don't care about anything else. Okay? Next part. I already forgot my own rules. What was the next rule? Electronegativity. What's the difference in electronegativity between oxygen and oxygen? Nothing. Next rule. Resonance. So to do resonance, we find typically the most reactive electrons, so usually a good place to start, and then we try and move those electrons. Everybody hates it when I do this, but I'm going to do it anyway. I'm going to start with that very first structure, and I'm going to move the electrons in. I'm going to attempt to do resonance. We can only move electrons from an atom to a bond, bond to an atom, or bond to bond. Our most reactive electrons are on the oxygen, on the atom, so I'm going to move them to that bond. Perfectly valid. There is nothing wrong with that. Right? What's the result? So now what we can do is draw out a temporary structure so that we can visualize what happened. Okay. Anything wrong with that? Okay, why are there too many bonds?
Because it's missing a hydrogen on the carbon.
We have to remember our implied hydrogens. They'll almost always haunt you. If we draw that in, we now have too many bonds. So the motion of the electrons in wasn't wrong. Okay, we moved them in and realized now we've exceeded the octet, so what we have to do is break a bond. What bonds are we allowed to break in resonance? Pi bonds. Do we have a pi bond to break? Yes. What's the result? Same thing you started with. You still attempted to draw a resonance. You just found that you didn't generate a structure that was stable enough to be drawn as a successful structure. Okay? Kind of makes sense? When you move to the next one, okay, we've got lots of resonance opportunities within the ring. Are those going to be good things to be looking at? I would say no. And the reason I would say no is, do I care about resonance within that ring? I'm comparing these two structures. I'm comparing where the negative charge is held. So the ring can have as much resonance as it wants, but if it doesn't impact that negative charge on the oxygen, it's completely irrelevant. Okay? So we want to find where our most common relationships are first and then push from there. So what we can do is move our electrons in, just like we did with our other one. And again, we can draw a temporary structure and try and evaluate what's going on with it. Do we have a problem with this structure? Yeah. What's the issue? Same. Is there an implied hydrogen? I know it was drawn a bit awkwardly in the first one. Our double bond is actually there. There are 5 bonds, so we still have that 5 bond issue. So what we need to do is fix our structure, because this structure is invalid. To do that, we need to break the weakest bond possible, or one of our weak bonds. What's the bond we're allowed to break? Pi bond. Do we have multiple pi bonds? Yes. Which one do we choose? The one that we didn't move already. Okay? And we can shift that out. Because our initial arrow was wrong, what we want to do is smash these into a single structure or a single step so that we can now evaluate again our overall result. Okay. We'd go through and evaluate our octet rules and find all our octet rules are satisfied, there's nothing wrong with it, which means we drew a valid resonance structure. What does that mean about the stability or the reactivity of the negative charge on the oxygen? It's more stable because that negative charge is now spread across multiple atoms as opposed to the one that it was in our first structure. So we can use resonance to explain the stability of that species. Okay? So what we said was that this guy was more stable. So if we're going to rank acidity, which compound is more acidic, left or right? Our right is more acidic. If we wanted to rank basicity, we'd probably shift to our conjugate bases here. Which one's more basic, left or right? Or we can call it A or B. For it to be basic, what does it need to do? The electrons must have only one escape to a hydrogen outside the structure. If we take a look at B, those electrons can shift into the structure. There's an alternate escape route, which means the B electrons are less reactive, which means weaker base, A's are stronger base. Okay? You'll notice that is what can be seemingly exceedingly tedious. That's fine. Okay? At this point, you're practicing it, getting used to drawing these things. If you've already see it, understand it, know it, good job. That's awesome. Okay? If not, continue to work through these things very, very slowly and do it enough times that by the time the exam shows up, they're easy. Okay? What happens if we go through and change our structures further? Okay, well, in our next one, this species ends up being even more acidic. Why? If you go through and draw your resonance structures, what you'll find is that this nitrogen out here starts to pull electron density, which means the electrons on the oxygen shift into the structure, which means that alcohol at the end becomes more acidic. Okay?
We compare it to the second one.
We can compare it to the second one. Or we even compare it to this one. If we wanted to rank acidity so far, this first one is more acidic than this one, more acidic than this one. Okay? Our 1 and 2 are currently so much more acidic that they end up getting classified by a different functional group name. We no longer refer to those as alcohols, even though we have an oxygen bound to a carbon. What functional group name do those get referred to as? Those two are phenols, whereas the first one was an alcohol. The chemistry between these two is very similar. You just have to realize the phenol is much more acidic. Right? And that's because of those resonance issues. If we shift to the very last one and evaluate what we've got out there, we still have that oxygen, hydrogen, and a carbon, just like we did with all our other ones. So we could still say, oh, this is an alcohol. Except what functional group is this? We call it a carboxylic acid. Why? It's an acid because that hydrogen is more acidic than it was in the alcohol. We get a different name for the functional group because we've changed its overall chemistry substantially enough that we give it a new name. Okay, so we can clarify it. When we go through and set up this, you can go through with the same ideas that you've been applying for everything else, and you will find that our ranking changes yet again, and we get our carboxylic acid being the most acidic all the way down. Okay? Go through and apply the rules, and you should see how those things or how those structures apply to generate that pattern. I will say the difference between the carboxylic acid and the nitrophenol is not as an easy of a delineation because there's multiple things contributing to the number 2 nitrophenol's acidity. Right? It's not just that we have resonance, but we also have this inductive withdrawing effect. There's a lot more things affecting its acidity.
So let me ask you a question.
Yes.
The way I kind of learned it was like this. We would kind of like just name what it would have, like element, and this one would have element. So am I doing it right?
Yeah.
Here?
So you're going through and you're ranking them exactly as we're talking about here. You're evaluating each of those stages where you see that difference.
Okay.
Yep. Okay. Other questions on the acidities? Yeah.
So the reason why the carboxylic acid is stronger because of the inductive effect?
There's a couple different ways you can look at it. You can look at it as induction. Whoops, if we remove the hydrogen first. So let's say that hydrogen isn't there. Got our negative charge. We can call it an inductive effect. We also have a resonance effect. Whoops. That was boneheaded. That was the same thing. Okay, why is this resonance better than, oh, I don't have any other resonance structures out there. Why is it better than for the phenols?
Because it goes on both the oxygen, right?
Where's our negative charge held? Our negative charge with our carboxylic acid is held on an oxygen in every single resonance structure. What happens with our phenols? Where's the negative charge held? On a carbon atom. Which atom can hold a negative charge better? Oxygen. So instead of looking at further on down our chain, once we've got our new resonance structure, we can shift back up to it and say, okay, where's our negative charge? Our negative charge is on oxygen versus carbon. That's, where is it? Not size, because we're in the same row. We'd be looking at an electronegativity difference. Okay? So
because it has the same basically resonance, that you can take a pi bond to either of the oxygens from both of them.
Mhm.
You look at the carbon and nitrogen's electronegativity, basically. You compare the nitrogen's electronegativity
So
to carbon.
I did not compare these two, our nitrophenol and the acid. That becomes more difficult to process because this group is now changing the chemistry around of this substantially. Evaluate your first resonance structure for stabilizing that oxygen. We put a negative charge on a carbon. What's this one do? Negative charge on an oxygen. Okay. More questions on the acidity? That was a great way to segue there. Repercussions. What's the result of having your alcohol act as an acid? What do you end up with? We get this species right here. What can you tell me is special about that compound? It is the conjugate base, which means we have that negative charge. What can you tell me about a species that has a negative charge? There we go. We've got it potentially acting as a nucleophile, or you listed off conjugate base. It could also act as a Bronsted base. Bronsted base would be pretty boring because we just did that. It would just be the reverse. But we could now have this species go through and react as a nucleophile with an electrophile. Okay? That's one of the big topics in the next chapter, chapter 14. Okay? Looking at the formation of ethers. I think I've got a slide here on it real quickly. The bottom one, what's the repercussion? We already talked about this. Evaluate what's out there. We now have a good leaving group. With a good leaving group, we can potentially see some substitution or elimination reactions. Okay, so it's identifying what things change about the structure. You don't stop after one step. You draw your products and you evaluate. What do those products do? What's the reactivity? Just like when we started, we looked at our starting materials, said the hydroxide in our first case is negative. It wants something positive. Do we have something positive? We got the hydrogen. Give it the hydrogen. What's the result? Now what happens? Okay. So organic chemistry, particularly second semester, is not one step and stop. It's one step, next step, next step, next step, next step. Do I have the answer yet? Next step, next step, next step. Do I have the answer? Okay, now I'm done. Okay. You must continue to process until you are done with the reaction. As far as figuring out when you're done, this is why it's nice to have multiple choice tests, because there's your answer. Okay. If it's not multiple choice, what should you evaluate? You need to look for something that makes it stable or unstable. What makes something unstable? Charge. If you see charge, that's usually a big red flag that something's wrong. See if you can find something within the structure to stabilize it. Okay, worst case, you push a bunch of stuff around and find out nothing stabilizes it. So what does that typically mean? That step is done, you add the next reagent. The next reagent then goes through and fixes whatever was unstable. Okay? So, synthesis of alcohols. So we're back to our alcohol, and I think this is a format I'm going to be happy with. So you'll see this again. we've got our overall alcohol functional group drawn out, and now what we want to do is evaluate how we could make this. Okay? So let's try and color code some of these things. How could we make the alcohol via substitution or an SN reaction? What bond would we be making? Good answer. We'll be making that carbon-oxygen bond. Okay? If we're going to do a substitution reaction, we can bring in that OH, okay, to supply or trade with an halide, as you did in your, I have no idea what chapter that is, your substitution chapters, and we now have an alcohol. What other options could we do? Anything else that looks familiar up there? The other one that you should be familiar with, which is, I know, arguably not true, we could also break a bond in the form of an addition reaction to get our alcohol. What bond would we be breaking? We'd be breaking a double bond in between our carbon atoms. How else can we get an alcohol? There's two other big reactions here which you have not seen in theory. We've got the Grignard reaction. The Grignard reaction is going to be making, let's add another carbon out here, making a carbon-carbon bond. Okay, that's an interesting one, not an easy one to make. We could also go through and break a bond in the form of a reduction. To go through and do that, definitely running out of colors. See how pink looks. If we're going to break a bond in the form of a reduction, anybody know what bond we'd break? We'd be breaking an oxygen-carbon pi bond. Okay? So what we're trying to identify is the different sections of reactivity. Where do these things fall? Why can we take advantage of these things? Well, that oxygen is electronegative. It causes a polarity shift, which makes our centrally located carbon very partially positive, which means we could then try and get some negative from an alkene, okay, through an addition, or if we looked at the reverse, an elimination. Okay. We could also evaluate adding that extra carbon-oxygen bond, that pi bond. That one's a little bit trickier to deal with because we aren't looking so much at charges. That one's a bit odd, so we'll come back to that. The oxygen is partially negative. Okay? So we've got the polarity within that alcohol structure. That polarity is really what's causing or allowing us to do the variety of reactions that we're going to try and play with. Okay? So let's look at a few of these. So we're going to make an alcohol via the substitution. There's two fancy arrows that we could look at or discuss here. So the one that you might be used to seeing is just a standard reaction arrow. Okay? But what we're looking at here is the synthesis of something. So another typical arrow, or commonly used one in this case, is what's known as a retrosynthesis arrow. Meaning we're going to start with our product and say we're going to work backwards to our starting material. Okay? If we're going to go through and do this substitution reaction, remember the bond that we said we were going to evaluate, assuming I color-coded properly, was that oxygen-carbon bond. Which means if we think backwards, what we'd be doing is breaking that bond. There's a carbon-carbon, there's that stuff. And we've got our oxygen-hydrogen out here. And our oxygen would have lone pair electrons. What happens to our carbon? Have to have some kind of positive charge associated with it. What charge is associated with our oxygen? Some kind of negative charge. So in the course of thinking backwards, we have to generate these pieces and try and come up with the best options. Okay? So our oxygen and hydrogen is going to be best supplied as what class? I know this is a new term. Okay, think reactivity. So it needs to be negative, so we could write that down. Our oxygen needs to be supplied as A negative. What species are negative? Nucleophiles, and I'm going to put bases, B bases in parentheses. Why not emphasize the Bronsted base? What do you want your oxygen to act as in this reaction to generate your alcohol? A nucleophile. If it acts as a Bronsted base, that's kind of counterproductive. We want it to be a nucleophile. Okay. How else can we figure out that we want it to be a nucleophile? It was known as an SN. What's the N stand for? Nucleophile. Okay. We take a look at the carbon, or that substrate. That's going to be best supplied as what class? So it's the same type of question. What charge should that carbon most likely come in as? Positive, which means it needs to act as an electrophile. So we've got the basics of that first step back. The big issue that we've got to watch out for is that we now look at those pieces. Are they particularly stable? No. Okay. Oxygen, we can kind of get away with a negative charge, because how could we supply an oxygen with a negative charge? Where have you typically seen that? Where have you typically seen that? Bronsted bases typically have big negative charge, say like sodium hydroxide. So we could supply that OH through sodium hydroxide. So that one's not too bad to stress about. But how often have you looked up at a reagent bottle and they give you a positively charged carbon? That doesn't really happen. So we have to come up with some way to stabilize that positive charge. But it still has to be positive. So what could we attach to it? Okay, we can't give it electrons. If we give it electrons, then it's not positive anymore. What if we put an extra carbon on it? What happens to the charge on that carbon? Neutralizes it. Why would you say it neutralizes it? I completely agree with you. What's the difference in electronegativity between carbon and carbon? Same, which means what's the partial charge on our target carbon? 0. That doesn't help. That does the wrong thing. Okay, let's try something else. Let's try a hydrogen. There's not a big enough difference between carbon and hydrogen to say the hydrogen's a valid thing to attach. We could go through and add a nitrogen or even an oxygen. The oxygen seems a bit redundant. Okay? But the problem with both of those functional groups is what else is attached to an oxygen or a nitrogen. We also get hydrogens potentially coming off. Why is that a problem? Now instead of doing one possible substitution, I've now put in positive hydrogens, which means acid-base chemistry. If I only want to do the substitution, I want to limit the presence of all other possible reactions. So whatever I attach better have only one chemistry, one bond, but still be able to take electrons away from that carbon. What am I left with? Halides. All of the halides. Okay, so we can do X as a halide. What functional group do we have? Alkyl halides. Okay, where you're looking at substitution and elimination reactions. Okay? So if we're going to try and make an alcohol via substitution, we can start with our alkyl halides and react them with an oxygen source. If we use straight up hydroxide, that's a great nucleophile, but it also comes in as a base. So that base characteristics can make it a bit dicey to deal with. Okay? The other thing that we could do is try a substitution one type reaction. So we could supply that oxygen in a more stable format, form of water, add that extra hydrogen. Problem with that, also have that acid-base characteristics with it. Which one's going to be better? Depends on what product you're aiming for. If you want a 100% one stereo center, which chemistry should you use? SN1 or SN2? 2, because SN1 gives you racemic products, okay, or a higher ratio of the racemic or the enantiomer. Okay, whereas SN2 is purely inversion. Okay? So you'd want to evaluate your final product and decide, do I care about the stereochemistry or not? Okay? And then you can adjust your conditions accordingly. Synthesis of alcohols. We could also break our bond via addition. So we could say that we were starting with an alkene. So we could drop in our retrosynthesis arrow, and we'd be looking at our same basic skeleton, except we would now have, did I do orange? I think I did orange. An alkene. So what things changed as we moved across from left to right? Our double bond disappeared. We also, whoops, that was pretty silly. Sorry. Said we were making it, right? Our oxygen bond appeared, and we also had a hydrogen bond appear. So we would want to go through and see what things were supplied and what's the easiest way to supply those. So the OH that we supplied, it's an eraser. What's the most likely charge on that oxygen? Most likely negative, because oxygen is more electronegative. We would expect it to be negative, which means it would typically come in as what class? A nucleophile. Let's just scribble through some of that, make it legible. Okay. We also added a hydrogen. What's the easiest way to get our hydrogen in there? H+. Okay, what's its class? Opposite of a nucleophile is an electrophile, but it's hydrogen, so we're looking at a Bronsted acid being the best way to supply it. So each of our reagents are going to try and supply each of these pieces in varying fashions. Okay? And that's what our alkene reactions are all about doing, or our addition reactions, is trying to get our alkene to react in such a fashion that we can get these two new pieces added onto it. Okay? So we could look, whoops, that's the non-obvious. So our standard obvious applications for this, we could go through and add H+ and water. The H+ gives us our H+. What does the water supply? That gives us ROH. Why do we have to add it as water, not as OH-? OH- is also known as strong base. What's the issue with a base, particularly in the presence of an acid? They neutralize each other, in which case we don't have our strong acid or our strong base. Our reaction doesn't work. All right? So we need to make sure that when we do this addition reaction that we're supplying H+ and water. We can't supply it as OH-. Okay? What H+ should we use? Strong acid, right? HCl. Is that a strong acid? Yeah. Why is HCl a bad option? Chloride's a leaving group, but it's not attached to anything that's going to make it important to act as a leaving group. It's also a nucleophile. The nucleophile we wanted was what? Oxygen, not chloride. So if we're going to go through and do the synthesis, an addition reaction using a strong acid, the acid we want to use would be one that has a non-nucleophilic conjugate base. Sulfuric acid is a big one for that. Okay. Let's see. I didn't break this down the way I wanted it. Other ways that we can get these pieces in here. What other reagents do we have? Actually, is that going to give me what I want? Can we get oxygen as an electrophile? What charge would the oxygen need to be? O+. Are we going to be able to do that? Interesting question, H3O+. does that supply oxygen as a positive charge? It is formally positive. Will it act as an electrophile? No. Why not?
We'll give that hydrogen oxygen.
There's a better answer. What happens if it acts as an electrophile? It has to accept electrons, right? How many electrons are currently around oxygen? 8. For it to act as an electrophile, it would have to accept 2 more. Is oxygen going to accept 2 more electrons over 8? No. So we have to be careful with formal charges. The formal charge does not necessarily tell you the reactive charge. Oxygen may be partially positive or formally positive here, but what about the electrons in those bonds? Where do they spend most of their time? On the oxygen, which means what happens to the hydrogen? Our hydrogen becomes our reactive positive. H3O plus will act as an acid, not as an electrophile. Good thing to point out. Whoever said that, good call. So oxygen acting as an electrophile, that may be non-obvious, but that's not going to happen. Okay. How about hydrogen as a nucleophile? For that to happen, what do we have to have? H minus. Okay. Not a lot of reagents supply H minus. Do we have one that you used perhaps last week in lab? Last week, yeah. Sodium borohydride. What's that? NaH, true, but that hydrogen is actually added as a base, believe it or not. It can't, the sodium hydride, the hydrogen there only functions as a base, not as a nucleophile. Sodium borohydride allows for slightly better stability of the intermediates in particular, which allows the hydride to act as a nucleophile in sodium borohydride. Sodium hydride doesn't have that. The sodium can't really do anything, okay, whereas the boron can. So we could supply a negative hydride, okay, but we'd still need to bring in our oxygen. We said the oxygen can't act as an electrophile. So what does that mean? The oxygen still has to be supplied as a nucleophile, but we have to somehow initiate in some way to get this reaction to work appropriately. The reagent we could go through and add. Our mercury acetate with water. Our water is what's supplying our nucleophilic oxygen. What is happening with the sodium borohydride? The hydride is being added as H minus, but it's being added to remove the mercury. Okay? So we're seeing a slightly different arrangement of what's happening with those chemistries. Those are, again, different possibilities. Okay? Other ways that we could get a hydride in there, or a negative hydrogen reacting. How about just BH3? What happens with BH3 and THF? THF is just the solvent, tetrahydrofuran. The boron has an empty p orbital that reacts with our alkene. Okay? Removing the negative of our alkene, the hydrogen from our BH3 can then get slid in as a hydride into our other position. So we end up running a pre-reaction. Our hydride is added to the alkene first. We then follow that up with something to remove the boron. Well, if we've got our hydrogen on, what do we need to add next? ROH. We can do that with peroxide and OH minus. Okay? So what we're trying to do is evaluate the different pieces that can potentially go into each of these and how each of those pieces get added. Okay? Different reagents are going to supply those pieces in different chemical fashions. You need to be somewhat familiar with what those pieces are and then follow that up with any stereochemical or regiochemical complications. Okay? What do we mean by regiochemical? We're looking at addition reactions, the standard phrase that comes along with it, Markovnikov, or the other option would be non-Markovnikov, as someone was talking about earlier. Right? You have to be familiar with what these reagents do as far as that regiochemistry on where it puts the hydrogen or the OH. That chemistry is based solely off of the resonance structures and the characteristics of each element, which is why you'll keep hearing me go back to what does that element have for electronegativity? What's its Lewis structure? Right? Because that understanding allows you to predict a lot of the chemistry. Okay? Questions? Another way we can get an alcohol on there, actually. One more. Could look at it as kind of a pre-reaction. Chandler Gilbert people apparently know it really, really well from the end of last semester. Br2 doesn't add a hydrogen or an oxygen. So what do we follow it with? We could end up with a bromohydrin or halohydrin if you do a different halogen. What's happening in that case, instead of you adding hydrogen, we'd be adding a bromine in place of it. Okay? So there's multiple ways that we can get the alcohols on here. You need to be familiar with those reactions, okay, or your alkene reactions. The next one, we could break it via reduction. Okay, so we actually have some new material here. What we're talking about in this case is looking at breaking that pi bond. So if we think retrosynthetically, what we're starting with is an extra pi bond out there. What is that going to do with the rest of our structure? What else has to happen? Also have to account for some other missing piece. Okay, one of those is going to have to disappear. Why? Have too many bonds around our carbon if we didn't get rid of one of them. Okay? So what we're going to try and do is reduce a carbonyl to the alcohol. So what we're going to do is get rid of one of those oxygen bonds. So what we're looking at is our redox reactions. If we think back to 151 or 152, we could go through and look at what is reduction. Well, reduction and oxidation are looking at changing oxidation states. So we could look at an individual molecule, say from Gen Chem, and determine the oxidation states of all of those elements. How do you do it? What's the oxidation state of the sulfur? Really hoping you'd walk me through that instead of doing it in your head. It's the oxidation state of our oxygens. -2, our hydrogens. +1, how do we know that? It's always like that, which is exactly right. We had it memorized that these were some standard oxidation states. So to figure out the sulfur, say the number of our hydrogens times its charge, plus the number of our sulfurs times its charge, which we don't know, plus the number of our oxygens times their charge, oxidation state equals our overall charge, which is 0. And we could then go through and solve for the oxidation state of our sulfur. Okay? That's nice when we have a centrally located atom. When we move into organic chemistry, we come into a problem. Maybe for the first one, we could solve that. Okay? What's the oxidation state of hydrogen? +1 for each of those, which means the carbon must be -4. What happens in the next one? Well, these were still all +1. Oxygen was -2. So our carbon has to be, come out at -2? I guess it does have to, which is why this becomes interesting. What we end up finding out, which makes this odd, is that oxygen being -2 is balanced by the carbon on one side and the hydrogen on the other. Is the hydrogen from our alcohol contributing to the oxidation state of the carbon? No, why not?
It's not attached.
It's not attached to it. Okay? So our standard format of going through and putting in all these charges, or all our oxidation sites and adding things up, isn't going to work. We have to come up with a different method. Okay? So what the textbook goes through and does is they have you evaluate each of the bonds. Okay? We're going to evaluate the electrons around the carbon. So in our first case, is carbon more electronegative than hydrogen? Okay, there's definitely two answers on that one. Yes, technically carbon is. It's not electronegative or more electronegative to make it to make it a polar bond. Okay? For the sake of this argument, it is more electronegative, which means where do the electrons in those bonds, particularly the ones that hydrogen brings in, spend their time? On the carbon, which means carbon now has an extra 4 electrons, which means it is -4. We move to the next one. We've got the electrons on those hydrogens. Let's go ahead and put one on that oxygen and take a look at the one that's going to be relevant. Our hydrogens are again lowered electronegativity than our carbon. Okay? So what happens with them? What happens with those electrons? Spend their time with the carbon. What happens to the electrons in the other bond? Spend the time with the oxygen. So carbon has picked up 3 electrons from our hydrogens, and we have, we'll look at just the electrons from the hydrogens that it's stealing from something else. -3. Okay? It can't take the electron away from our oxygen. If we move to the next one, what happens? It can take the electrons away from our hydrogens. Can it take the electrons away from the oxygen? Nope. What do we end up with? -2. What happens in the next one? -2. But there's a double bond. Does that change anything? Nope, it's still an oxygen. I don't care. Next one. That was fun. It was the exact same thing. I'm pretty sure I was supposed to change that. Here, let's change that real quickly. I'm going to say those were supposed to be carbons. Is that what I was going to say? I guess one of them was a carbon. What happens? Now we're looking at -1. Wait, where did you go? Come back here. -1. So the idea, and then your textbook is going to explain this much better because they actually trust this method. I don't, because I get it wrong every so often, is evaluating each of those charges and each of those effects. And then when we want to figure out what happened, we could look at our oxidation states and decide, well, whether that was an oxidation reaction or that was a reduction. So we could go back and apply these rules. The other option is we could start to look at something a little bit more common, which will be more relevant for us in this class at this point. Reduction is an increase in hydrogen bonds. It can also be associated with a decrease in oxygen bonds. So we are reducing the oxygen content. If we go through and look at oxidation, it's an increase in the oxygen bonds or a decrease in our hydrogen. Okay? That can help us then go through and evaluate individual reactions and try and decide how do our oxidation states shift, and are we in a redox reaction or not. Okay? So what I would expect you to be able to do with some success is to be able to go through and apply different examples and decide, was it a reduction reaction or an oxidation reaction, or potentially neither. And a lot of that comes back to evaluating all of these potential rules as we go through and look at them. So for our very first step, very first one, what happened? All right, if we evaluate here. could go through and look at all those rules. We lost a hydrogen atom. Okay, because we go and look at that carbon. So a hydrogen was lost, so we decreased the hydrogens. So that would suggest oxidation. We don't need to go through and evaluate each of the individual charges to determine that. We can just look at what changed. If we move to the next one, that one's a little bit trickier. Actually, I don't think it's that much trickier. What happened as we shifted across that reaction? We lost hydrogen. So what happened? Oops. Our first one was oxidation, not reduction, wasn't it? Sorry. Okay. So we can either quickly evaluate just based on these other rules to kind of shift through it, or we can go through and apply each of those individual oxidation states. The ones that are going to be particularly relevant, unfortunately I didn't, at least for our case right now, would be the reverse of this one. What happened in this reaction? Now in red. What happened to the hydrogens around our carbon? We lost them, so we have what kind of a reaction? Oxidation. What do we want to do? We're looking at trying to make alcohols. We want to do the reverse of an oxidation, which is reduction. How can we go through and do that? Well, we'd evaluate again our structure and try and decide what things changed. We got a hydrogen there and a hydrogen up there that had to get added to the structure. And we also had to break our pi bond somehow. Our oxidation and reduction reactions are a bit tricky to kind of deal with. Okay? Some cases, they're a little bit easier to see than others. If we go through and look at the reactivity of our starting material, do you see anything that jumps out at you as far as polarity of each of those bonds? One thing that I see is I see an oxygen. Oxygen is highly electronegative, which means its charge is going to start to be partially negative. Where is it getting those electrons from? That pi bond, which means that carbon right underneath it needs to be partially positive. So if I'm going to bring in hydrogens to do this reduction, those hydrogens need to be distinctly different because they're interacting with different atoms, different partial charges. The one on top needs to be coming in as an H+. That's really easy to supply. I can supply that with an acid. The H on the bottom, on the other hand, is a bit different. It needs to come in as an H- or a hydride. Okay? That's not particularly easy to get in there. We want to supply something that can give us hydrides. Already you should know one reagent that's going to give us these two hydrogens. Anybody remember what that one reagent is?
NaBH4.
Okay, that's cheating. You should know two reagents. H2, hydrogen gas with platinum and palladium. Completely non-selective reduction. Hydrogen adds to any pi bond. Okay? We also have another reagent, sodium borohydride. That reagent will supply hydride ions, which is the trickier part of this, is that hydride, getting that in there. Okay, so we end up with three possible sources for these. Okay, our first one, I should have switched the order around. First one that you guys have seen has been sodium borohydride. We saw that in the lab. Okay, and we could follow that up with, or run that reaction in water or in alcohol. What did the water and the alcohol supply? Our positive, whoops, forgot it's gotten rid of. They supplied our positive hydrogen. Okay, whereas our borohydride supplied our negative, our hydride. We could also run another reaction. We could use lithium aluminum hydride. Very, very similar chemically. Okay? Where is sodium? First column of the periodic table. Where's lithium? Same column. Where's boron? Third column. Where's aluminum? Third column. The chemistry between those two is almost identical. The subtle differences between them end up changing the specificity or the reactivity of each of these. Lithium aluminum hydride is much, much more reactive. So much more so that we have to add water as a second step. If we added it with the lithium aluminum hydride, it would immediately give up its hydride ion as a base, react with our water, and we don't get our nucleophilic reaction. Okay, so we have to do it in two steps. Our water addition at the end will both quench any leftover lithium aluminum hydride and also add us our H+ to get us our final alcohol. Okay? Hydrogen with our metal catalyst. I don't want to go through this a whole lot, but the platinum catalyst allows for the flow of electrons, hence a metal. Your alkene will bind to the metal. Those electrons kind of shift into our metal cloud, and our hydrogens will also interact with our platinum catalyst in such a fashion that the hydrogen can then react with our alkene, and we end up with our final alkane product. The problem with hydrogen and a metal catalyst is that it's not selective for our carbonyls, which means if we have an alkene also in our structure, also reduced. If we wanted that alkene, that's a bit of a problem. Okay? If we had an alkyne, same issue. It's going to reduce it. So what we would like is a better reagent. That's where our sodium borohydride in water can come into play. Remember, boron has that empty p orbital. That empty p orbital, in the case of sodium borohydride, can hold on to 2 electrons from another hydrogen. Okay? Boron doesn't really want those electrons in there. So what it can do is start to saddle up next to a double bond, particularly a carbonyl, and shuttle that hydride into our carbonyl. Okay? Why does it work in this case as opposed to the other cases? Okay? Why does it not react with an alkene? In the case of an alkene, we don't generate enough of a partial charge differential between the two atoms. In the case of a carbonyl, we have that large differential between our oxygen and our carbon. There's already a lone pair on that oxygen. So what can happen is our boron can saddle up right next to that oxygen. Okay, why does that help? Well, boron can then, as it releases the electrons from our hydrogen, or our hydride, can also accept electrons from the oxygen, helping to kick off our hydride and allowing it to react. So one of our intermediates is something related to this, where we now have our hydrogen attached. We want to get rid of the boron. That can be done with a little bit of heat in the presence of a weak acid, something like water or an alcohol. And that will then kick off our boron, and we'll be left with our alcohol. Okay? So it's the chemistry of that empty p orbital, or that potentially empty p orbital on our boron, that really pushes this chemistry. Okay? It will react with ketones and aldehydes. It won't react with other carbonyls. What other carbonyl-containing functional groups are there? We have esters, carboxylic acids. Okay? It won't react with those. So if we have an aldehyde, our sodium borohydride is relatively nice. We can throw that in there and get it to go. Okay? Why would we use this and not, say, something like lithium aluminum hydride? Where'd it go? Well, number one, it only reacts with our aldehydes and ketones. So we don't have to worry about it reacting with other things and getting in the way. The other thing that's nice about it is we can use simple solvents like water or alcohol. If we jumped up to lithium aluminum hydride, it's so much more reactive that we can't use simple solvents like that, lower toxicity. We'd have to pick other solvents that are potentially more dangerous. So in most cases, when we go through and try and run a reduction, we'll push for sodium borohydride. Why would we not? Well, maybe we can't use water or alcohol. Maybe there's another reactive group somewhere in that structure. Okay? There's something going on with our compound that prevents it from reacting with the borohydride. Okay? But borohydride is going to be our primary reducing agent. The other option is using something like lithium aluminum hydride. It reacts very, very similarly. Remember, it's the same kind of structure as our boron. The aluminum can saddle up on our oxygen side, and it can release our hydride on the carbonyl side, and we can end up with our nice happy transition state just as we did before. And then we can follow that up with our water addition to help react and then kick off the aluminum hydride. Okay? The problem with our lithium aluminum hydride is that it is very, very reactive. So we have to use different solvents, and it'll react with all carbonyls, including our esters, which are shown here. We've got an ester functional group, and potentially carboxylic acids. No, it won't react with carboxylic acid. Why not? What does the carboxylic acid also supply? That hydrogen. What did we say about the reactivity of lithium aluminum hydride? Ridiculously reactive in the presence of acids, like water and alcohol. Okay? A carboxylic acid is even more acidic, which would suggest it's just going to pull off that hydrogen. Okay? What's the result of the reduction with an ester? Whoops. We can go through and push this out, and we get our alcohol. We'd have this. This is a particularly interesting functional group that we'll see at the end of the semester. We're done at 55. Yeah. It's known as a hemiacetal. Very, very unstable. Okay? It tends to fall apart rather readily. What ends up happening is that central carbon has a lot of electron density being pulled away from it. So what we end up seeing is a lone pair on our oxygen coming down and kicking out that other group. What's interesting about that? What do we end up with? We'll do that proton transfer. What functional group do we now have? Close, not quite. I guess it's not directly specified. We've got a ketone or potentially an aldehyde. Okay, in this case, we would end up with an aldehyde. Okay, why is that a problem? What does the aldehyde then do in the presence of lithium aluminum hydride? It reacts. So what ends up happening with an ester is we end up with two reductions. We turn it all the way down to both alcohols. So our ester gets reduced completely out. Okay? So that's one of the things that we need to be concerned about when we're dealing with lithium aluminum hydride. I didn't talk fast enough. So why is lithium aluminum hydride faster than sodium borohydride? Okay, it's not super critical that we evaluate this, but you should start to come up with some ideas. What do you think? If it's more reactive, what are we saying about the hydrogen on lithium aluminum hydride versus a hydrogen on sodium borohydride? I know where you're getting at, but that's not the question I asked. We said about the hydrogens first. The hydrogen on lithium aluminum hydride must be more negative, or a bigger negative than the other one. Okay, why? That's what makes it reactive. The more charged it is, the more reactive it becomes. So why is the hydrogen on lithium aluminum hydride more negative than on the other one? So we could try and then evaluate where is it getting those electrons from? Aluminum versus boron. electronegativities aren't going to help us, but size will help us. Aluminum is massive, which means that hydride, or that aluminum hydrogen bond, and now instead of being really small, is now much longer, which means it does what to the strength of that bond? It weakens it. The longer the bond, typically the weaker it becomes. So what does that mean? Our hydride is then easier to react, easier to pop off because it's not being held as tightly. Okay, so that's one way we could evaluate it. Where's another big difference? I personally think it's a small difference, but we could look at the sodium and the lithium. Lithium is smaller, meaning it's going to be a better Lewis acid, so it's going to coordinate much tighter with our carbonyl. Why does that matter? Let's call this our metal. If we make this bond stronger, what does that do to this bond? It weakens it. Oxygen doesn't want to have 3 bonds. So if we put in a really strong Lewis acid out here, our metal, this bond weakens and we start to approximate this structure. Why is that important? What does that do to the reactivity of the carbon? It makes it more reactive. It's now more positive. So we've got 2 ways that we can describe this. We can look at our Lewis acids, our metal ions, making our carbon more positive, or we can look at our hydrides being more negative because of the bond difference or the bond length difference between aluminum hydride and borohydride. Okay? So all we're trying to do is evaluate those differences and come up with some theory to explain it. It's what you're doing with everything you're doing this semester. Identify that difference and see how that works to explain the difference in the results. Okay? We'll end this real quickly on this slide. What's our result if we react it with sodium borohydride?
With the left carbonyl, or oxygen, get the hydrogen.
Okay, that is one way to describe it, and I will agree with that. What's another way to describe that carbonyl? Ketone. Why can we call it a ketone? What's the issue with the other carbonyl? Which means it is an ester. Okay, so we've got the ketone carbonyl versus the ester carbonyl. So in the case of sodium borohydride, we just reduced that one position. What happens with our lithium aluminum hydride? It's still going to reduce our guy out there, our ketone. It will also reduce the ester. And the process of reacting with the ester, though, it's going to end up cleaving our ester bond and turn that into an alcohol as well. Okay, remember, the ester has to react twice. We end up with that hemiacetal intermediate, which falls apart. What happens in the last case? All of those reductions occur, and that's not an A. We react the double bond. Okay? So all of those individual things occur and process. You have to be aware that each of those reagents is going to do something slightly different. You've got to be careful with what you're trying to do and evaluate all of the reactivity within the structure. Your simple examples will only have one functional group. As the semester goes, you're going to see more and more functional groups show up. You have to remember that each of these reagents does something slightly different. Okay? Definitely nowhere near as far as I wanted to get. And because I think we are behind, I know you're going to love this, I'm going to record another lecture and I'll post that to YouTube so you've got access to that. Okay? We will go through over some of the basics, but I'm going to put the bulk of it in a secondary lecture on YouTube probably Friday. alkyl. So please watch that video. I'll put a link on it so you've got access to it. I need to kind of make up for the alkene review that we're sliding through at the beginning.